Welcome to Sleepy Science. In this video, we're diving deep, very deep, into the world of science. But not just any science. We're talking about the origins of sciences themselves. How do entire scientific fields come into being? Did the people who started them know what they were doing? Or were they just curious minds following questions to their natural and sometimes accidental conclusions? Over the course of this video, we'll calmly explore how science evolved, from ancient philosophy and religious traditions to today's data-driven global research. We'll look at early thinkers who never called themselves scientists, revolutions that reshaped the world, and the modern rise of new disciplines like AI, neuroscience, and sustainability studies. Each section is a slow-moving stream of thought, backed by history, logic, and a love for big questions. So settle in, grab a warm blanket, maybe a cup of tea. This is not a high-speed lecture. There are no pop quizzes, just a gentle, thoughtful journey through the making of science itself. And if you enjoy this style of quiet, thoughtful content, don't forget to subscribe, give the video a like, and maybe share it with a fellow knowledge lover who could use a bit of peace with their learning. Now take a deep breath, and let's begin. The question of how sciences were created, and whether those who contributed to them were aware of their monumental role, touches on both the history of human knowledge and the psychology of discovery. It's a topic that seems to belong equally to historians, philosophers, and scientists themselves. To tackle it properly, we must admit up front, science did not suddenly descend from the heavens, fully formed, wearing a lab coat and carrying a beaker. It was a messy, slow, fascinating evolution of ideas, methods, and accidental brilliance. Before diving into the rich and occasionally chaotic chronology of science's development, we need to establish the stakes. This isn't just about honoring the past. It's about understanding how knowledge works, how it begins, how it spreads, how it solidifies into disciplines. By dissecting this process, we not only recognize the geniuses who dared to ask, "Why does the apple fall?" but also come to terms with how accidental, unintentional, and occasionally ridiculous progress can be. And yes, spoiler, a good number of scientific breakthroughs happened because someone was curious, or stubborn, or simply bored. Science, as a concept, is deceptively simple on the surface. In everyday language, it refers to the pursuit of knowledge about the natural world. However, when examined more deeply, science reveals itself to be a highly structured and dynamic system of understanding, grounded in empirical observation, theoretical formulation, and methodical testing. To understand how sciences were created, and whether their creators were aware of their role in shaping them, it is essential first to define what science is and identify its fundamental characteristics. At its core, science is a systematic enterprise that builds and organizes knowledge in the form of testable explanations and predictions about the universe. This definition emphasizes a few crucial aspects: systematization, knowledge, testability, and predictive power. These elements distinguish science from other forms of human inquiry such as art, religion, or philosophy, which may seek meaning or truth, but often do so through subjective, interpretive, or non-empirical means. The word science is derived from the Latin scientia, meaning knowledge. In its modern usage, however, science is more than just accumulated facts or observations. It involves a specific way of thinking, a methodological approach that includes observation, experimentation, hypothesis formulation, testing, and refinement. This process is often referred to as the scientific method, although it is better understood not as a rigid formula, but as a flexible, iterative framework that guides investigation. One of the defining features of science is its reliance on empirical evidence. This means that scientific claims must be based on observable, measurable phenomena. In other words, science is grounded in the real world. It depends on data that can be collected, analyzed, and verified. This distinguishes scientific knowledge from speculation or opinion. While imagination and creativity are essential in developing hypotheses or models, those ideas must ultimately be subjected to empirical scrutiny to be considered scientifically valid. Another key characteristic of science is its commitment to objectivity. In theory, scientific inquiry seeks to eliminate bias, focusing on facts rather than personal beliefs or values. In practice, complete objectivity is difficult to achieve, as all researchers bring their own perspectives, assumptions, and cultural influences. Nevertheless, science employs various mechanisms, such as peer review, replication, and transparency of method, to reduce subjective influence and ensure reliability. This collective self-correction is one of the great strengths of the scientific enterprise. Science is also characterized by its systematic nature. Scientific inquiry does not proceed in a random or haphazard manner. It follows a disciplined process aimed at understanding causal relationships and uncovering underlying principles. This systematization enables the building of coherent theories, frameworks that explain diverse phenomena and connect isolated facts into a broader understanding. For example, Newton's laws of motion are not merely descriptions of how objects behave. They are part of a theoretical system that explains motion across a wide range of contexts. Importantly, science is inherently provisional. Scientific knowledge is never considered final or absolute. It is always subject to revision in light of new evidence. This is not a weakness, but a strength. It allows science to adapt and improve over time. Theories that were once dominant can be modified or replaced as new discoveries are made. For example, classical mechanics was supplanted in part by quantum mechanics and relativity, which offer more comprehensive explanations in certain domains. This openness to change is a core feature of scientific thinking. Furthermore, science aims for generalization. It seeks to discover laws or principles that apply across multiple instances or cases, rather than explaining isolated events. A scientific theory gains power not only from its accuracy in a single case, but from its ability to explain and predict phenomena across different contexts. For example, the law of conservation of energy applies to chemical reactions, mechanical systems, and even biological processes, demonstrating the unifying capacity of scientific principles. Predictive capability is another important feature of science. Beyond explaining existing phenomena, science endeavors to forecast outcomes under specific conditions. These predictions are based on established theories and tested models. For example, weather forecasting, while not always precise, relies on complex scientific models involving physics, atmospheric science, and computational algorithms to predict future weather patterns. In more controlled environments, such as physics experiments, predictions can be even more precise, often to many decimal places. Another distinguishing trait of science is its communicability. Scientific knowledge must be articulated clearly and shared with others in a way that allows replication and critique. This is why formal publication, data transparency, and methodological disclosure are so important in the scientific community. Unlike some forms of esoteric knowledge or personal revelation, science must be open and accessible, at least in principle, to any qualified individual who wishes to examine or test its claims. It is also important to note the role of mathematics in science. While not all sciences are equally mathematical, mathematics often serves as the language through which scientific theories are expressed. It provides precision, clarity, and the ability to model complex systems. In disciplines like physics and chemistry, mathematical equations are central tools for formulating laws and making predictions. Even in fields such as biology or psychology, statistical methods are essential for analyzing data and testing hypotheses. Finally, science is a collective endeavor. While individual contributions are vital, science advances through the accumulation and integration of many efforts over time. No scientist works in isolation. Their work builds on prior research, and their findings become part of the shared body of knowledge that others can use, refine, or challenge. The scientific community plays a crucial role in maintaining standards, evaluating claims, and fostering progress. It is through this community that science becomes more than a personal pursuit. It becomes a social institution with its own norms, practices, and structures. In conclusion, science is a systematic, empirical, objective, and provisional mode of inquiry aimed at understanding the natural world. Its core characteristics, reliance on evidence, systematization, predictive power, and communicability, distinguish it from other forms of knowledge. Understanding these characteristics is essential for grasping how scientific disciplines emerged and how individuals, often unknowingly, contributed to the construction of what we now recognize as science. This foundational understanding will serve as a basis for the subsequent sections, which will explore how this complex and powerful way of knowing evolved from ancient origins to modern institutions. The origins of scientific knowledge can be traced back to the earliest stages of human development, long before the concept of science as we know it existed. Long before laboratories, equations, or peer-reviewed journals, humans were observing the natural world, experimenting with tools, tracking the movements of stars, and drawing conclusions about cause and effect. The birth of science, in this sense, did not occur at a single moment in history, nor was it the work of a single civilization. Rather, it was the gradual accumulation of observations, experiences, and explanations that slowly became more systematic over time. In early human societies, knowledge was deeply intertwined with survival. Early humans needed to understand their environment in order to hunt, gather, navigate, and build shelter. Trial and error formed the earliest method of empirical learning. If a certain plant caused illness, it would be avoided in the future. If another alleviated pain, it might be remembered and used again. This rudimentary form of knowledge, based on direct experience and practical necessity, laid the groundwork for later, more formal systems of inquiry. However, in these early societies, knowledge was not separated into distinct domains. What we now call medicine, astronomy, or engineering existed within a larger framework that included myth, religion, and ritual. For example, the movements of celestial bodies were observed and recorded not as a means of understanding astrophysics, but as a way to predict seasonal changes or interpret divine will. This blending of empirical observation with spiritual or supernatural interpretation characterized much of early human knowledge. Oral traditions played a crucial role in the transmission of this knowledge. Before the advent of writing systems, information was passed down through storytelling, songs, rituals, and apprenticeship. While this limited the complexity and precision of the knowledge, it ensured its survival across generations. Over time, as societies became more complex and urbanized, the need for more precise, organized, and permanent records of knowledge grew. The development of writing around 3200 BCE in Mesopotamia marked a turning point in the history of knowledge. With written language, it became possible to record observations, transactions, and ideas in a permanent and standardized way. This allowed knowledge to be accumulated, compared, and transmitted across distances and generations with greater fidelity. The earliest written records include astronomical observations, medical prescriptions, mathematical calculations, and administrative data, all of which point to the emergence of structured forms of knowledge that would later evolve into science. In ancient Egypt and Mesopotamia, we see the first glimpses of systematic approaches to problem solving. Egyptian medicine, while still steeped in religious belief, included diagnostic techniques, surgical procedures, and pharmacological recipes. Babylonian astronomy involved the careful recording of celestial events and the development of complex mathematical models to predict eclipses and planetary movements. These civilizations demonstrated that, even in the absence of a fully developed scientific method, it was possible to engage in sustained, cumulative investigation of the natural world. In ancient India, scholars made significant advances in mathematics, metallurgy, and medicine. Texts such as the Sushruta Samhita detailed surgical techniques, while mathematical works introduced concepts like zero and advanced geometry. Similarly, in ancient China, observations of nature were deeply integrated into medicine, agriculture, and engineering. The Chinese also developed sophisticated methods of categorizing herbs, diagnosing illness, and tracking astronomical phenomena, often combining empirical techniques with philosophical frameworks such as Taoism and Confucianism. Although these early forms of knowledge were not science in the modern sense, they shared several important characteristics. They were based on observation, aimed at practical outcomes, and transmitted through structured systems. What they often lacked was a formalized methodology for testing hypotheses and separating objective evidence from cultural or spiritual interpretation. One of the most important factors in the development of scientific knowledge was the increasing capacity of societies to specialize. As populations grew and labor became more divided, certain individuals could devote themselves entirely to the study of specific phenomena, be it the stars, the human body, or the behavior of materials. This professionalization of knowledge created a foundation for the eventual emergence of distinct scientific disciplines. The role of philosophy in shaping early scientific thinking cannot be overstated. In many ancient cultures, especially in Greece, India, and China, philosophical inquiry laid the foundation for more formal scientific reasoning. Philosophers questioned the nature of reality, causality, and the reliability of sensory experience, all of which are fundamental concerns in science. Although philosophical approaches were often speculative and abstract, they introduced the idea that the world could be understood through reason and logic, not just tradition or divine revelation. As societies developed writing, mathematics, and philosophy, their knowledge systems became increasingly complex. These developments set the stage for the emergence of what we would recognize as proto-scientific thought. For example, early geometry emerged from practical needs such as land measurement, but evolved into abstract theorizing about space and form. Early medicine moved from magic and ritual to systematic observation of symptoms and treatments. Astronomy developed from calendrical and agricultural needs into sophisticated models of celestial motion. It is important to emphasize that early knowledge systems did not necessarily aim to discover universal truths. Rather, they were concerned with managing uncertainty, predicting outcomes, and maintaining social and cosmic order. In this context, the role of science was not yet to challenge beliefs or develop independent theories, but to serve practical and often religious purposes. Nonetheless, these early forms of knowledge contained the seeds of scientific thinking. The practice of careful observation, record-keeping, hypothesis formation, even if informal, and transmission of methods formed the essential groundwork for future scientific revolutions. The notion that the world operated according to discernible patterns, and that those patterns could be studied, recorded, and eventually predicted, was a powerful one, even if it had not yet been articulated as science. In conclusion, the origins of scientific knowledge are deeply embedded in the earliest stages of human culture. While ancient knowledge systems were not scientific in the modern sense, they exhibited many of the features that would later define science: empirical observation, systematization, cumulative transmission, and practical application. By recognizing the depth and diversity of early knowledge traditions across civilizations, we gain a broader and more inclusive understanding of how science emerged. not as a sudden invention, but as a gradual evolution of human curiosity and ingenuity. The foundations of science were laid not by a single culture or civilization, but through a slow, collective accumulation of ideas and observations developed across various regions of the ancient world. Among the most influential contributors to early scientific thought were the ancient civilizations of Egypt, Mesopotamia, India, and China. These societies, each in their own way, engaged in systematic inquiries about nature, the cosmos, medicine, and mathematics, creating the intellectual groundwork upon which later scientific traditions would build. While the motivations for this knowledge were often practical or religious, their long-term effects were transformative, influencing generations of thinkers across time and space. In ancient Egypt, knowledge was deeply connected to religion and the bureaucratic needs of a centralized state. The Nile River dictated much of Egyptian life, and understanding its cycles was essential for agriculture and planning. As a result, Egyptian priests developed an early form of calendar based on astronomical observations. They divided the year into 365 days, grouped into 12 30-day months, with 5 additional days at the end. This calendar was used not only for agricultural purposes, but also to determine religious festivals and rituals. Medicine in Egypt was another area of early scientific development. While Egyptian medicine was often framed within religious and magical contexts, it also displayed an empirical side. Medical papyri, such as the Edwin Smith and Ebers papyri, include descriptions of diagnoses, symptoms, surgical procedures, and herbal remedies. Egyptian physicians observed wounds, classified diseases, and described internal organs based on human dissection, though dissections were rare and largely symbolic due to religious taboos. Despite these limitations, their approach to medicine was systematic and surprisingly detailed. Mathematics in Egypt developed from practical necessities. Land surveying, taxation, and construction required accurate calculations, especially in the aftermath of Nile floods that erased property boundaries. Egyptian engineers designed impressive structures such as pyramids and temples using basic geometric principles. They understood arithmetic operations, geometry for measuring area and volume, and used unit fractions to perform calculations. While not theoretical in the way Greek mathematics would later become, Egyptian math was applied and consistent, grounded in real-world use. Mesopotamia, located in the region between the Tigris and Euphrates rivers, developed one of the earliest written scripts, cuneiform, and used it extensively to record astronomical, mathematical, and medical knowledge. The Babylonians, in particular, achieved remarkable precision in astronomy. Using clay tablets and simple instruments, they tracked the movements of celestial bodies, identified planetary cycles, and predicted eclipses. Their work was not yet based on physical theories, but on empirical patterns derived from centuries of observation. They developed a sexagesimal, base, 60 number system, which is still reflected today in how we measure time and angles. Mesopotamian medicine, similar to Egypt's, included both magical and empirical elements. Healers, often priests or scribes, compiled handbooks listing symptoms, diagnoses, and recommended treatments. These texts followed a structured approach, listing conditions alongside probable causes and effects. Although treatments were often mixed with religious incantations, the presence of pattern recognition and classification indicated a rudimentary scientific approach. In India, scientific thought developed alongside deep philosophical traditions. The ancient Indian civilization contributed significantly to mathematics, astronomy, and medicine. One of the earliest Indian texts, the Sulba Sutras, written around 800 to 500 BCE, contains geometric principles necessary for constructing altars. These texts demonstrate knowledge of the Pythagorean theorem well before Pythagoras himself, suggesting that mathematical ideas developed independently in different parts of the world. The concept of zero, so fundamental to modern mathematics, is one of India's most influential contributions. Indian mathematicians also developed the decimal system, algebraic methods, and trigonometric concepts. Scholars like Aryabhata and Brahmagupta advanced mathematical and astronomical theory, proposing heliocentric ideas and discussing the Earth's rotation long before similar ideas emerged in Europe. Indian medicine, recorded in texts such as the Charaka Samhita and Sushruta Samhita, laid the groundwork for Ayurvedic science. These works included detailed anatomical descriptions, classifications of diseases, pharmacological knowledge, and even surgical techniques. Sushruta's text, for example, describes over 300 surgical procedures and more than 100 surgical instruments. Indian physicians emphasize diagnosis, patient history, and hygiene, principles that resonate with modern medical practices. In ancient China, a similar fusion of practical knowledge and philosophical inquiry led to early scientific development. Chinese astronomers, like their Babylonian counterparts, kept meticulous records of celestial events. Observations of comets, eclipses, and planetary movements were often tied to political and astrological interpretations, yet the precision of the data remains a testament to their observational skills. The Chinese also developed star maps and mechanical models to represent the heavens. Chinese medicine, with its emphasis on balance and harmony, focused on the body's internal systems and their relationships to nature. The Huangdi Neijing, the Yellow Emperor's inner canon, compiled in the first millennium BCE, presented a complex model of human physiology based on the flow of qi, energy, and the interplay of yin and yang. While these concepts differ from Western biomedical frameworks, the text includes careful observation of symptoms, classification of illnesses, and principles of diagnosis and treatment. One of China's most impressive scientific legacies lies in engineering and invention. The ancient Chinese developed technologies such as the seismograph, the magnetic compass, gunpowder, and papermaking, all of which had lasting impacts on the world. These inventions were not isolated. They resulted from systematic experimentation, accumulated experience, and problem solving. The Chinese also practiced early metallurgy, developed crop rotation methods, and created hydraulic systems for irrigation, all of which required precise and reliable technical knowledge. What unites these ancient civilizations in their approach to science is their reliance on observation, record-keeping, and practical application. While their understanding of the natural world was often embedded in religious or cosmological systems, their knowledge was far from arbitrary. They recorded data, looked for patterns, tested techniques, and passed knowledge through education, apprenticeships, and written texts. This cumulative approach created a foundation upon which later civilizations, including the Greeks, Romans, and Islamic scholars, would build more formalized systems of scientific inquiry. It is also crucial to recognize that early scientific ideas were not always recognized as such by those who practiced them. There was no word for science in ancient Egypt, Babylon, India, or China. The modern conception of science as a distinct, autonomous activity only emerged much later. But if we judge by function, the pursuit of reliable, systematic, and transferable knowledge about the world, then these civilizations undoubtedly engaged in what we would now identify as scientific activity. In summary, the birth of scientific ideas did not happen in isolation or in a single place. It emerged from the collective and overlapping achievements of ancient civilizations that developed systems of knowledge to understand their environment, manage health and agriculture, and predict natural events. Their efforts reveal that the roots of science are both older and more global than often assumed. By exploring their contributions, we gain a deeper appreciation for the complexity and diversity of early human inquiry, and for the enduring human drive to understand the world. While many ancient civilizations laid the groundwork for scientific thought through practical innovations and empirical observations, it was in ancient Greece that science began to transform into a systematic and theoretical enterprise. Greek thinkers shifted the focus from solely observing and recording the world to asking why it functioned the way it did. This new emphasis on rational explanation, logical argument, and the search for universal principles marks a critical turning point in the development of science. The contributions of Greek philosophers and mathematicians continue to shape modern scientific thinking, both in method and in substance. The Greeks did not view science as a separate field of study, distinct from philosophy or mathematics. Instead, what we now call science was considered a branch of philosophy, specifically natural philosophy, the study of nature and the cosmos. This integration of philosophical reasoning with empirical observation is one of the defining features of early Greek thought. While their tools and technologies were limited, their intellectual ambition was vast, to discover the underlying principles governing all things. One of the earliest known Greek philosophers was Thales of Miletus, who lived in the 6th century BCE. He is often credited as the first person to propose a non-mythological explanation for natural phenomena. Thales suggested that water was the fundamental substance of all matter, not because of religious belief, but because of its observable presence in life and nature. While his hypothesis was ultimately incorrect, the method he used, attempting to explain the universe through rational, natural causes, was revolutionary. Following Thales, a series of thinkers known as the pre-Socratic philosophers began exploring the nature of reality, matter, and change. Anaximander proposed that all things emerged from a boundless, indefinite substance, a pyrrhon, while Heraclitus emphasized change and flux as the fundamental features of reality. Parmenides, in contrast, argued that change was an illusion and that true reality was unchanging and eternal. These conflicting views may seem abstract, but they laid the groundwork for later debates about matter, motion, and the structure of the universe. Perhaps the most influential figure in early Greek science was Pythagoras. Best known for the mathematical theorem that bears his name, Pythagoras was also a philosopher who believed in the fundamental role of numbers in the structure of the cosmos. For the Pythagoreans, mathematics was not just a tool for measurement, but a key to understanding the harmony and order of the universe. This belief in the deep connection between mathematics and reality became a central principle of scientific thought, continuing into modern physics and cosmology. The transition from speculative philosophy to more systematic observation began to take shape in the work of Hippocrates and his followers in the 5th century BCE. Often called the father of medicine, Hippocrates sought to understand health and disease through careful observation of symptoms and environmental factors, rejecting supernatural explanations. The Hippocratic Corpus, a collection of texts attributed to him and his school, emphasizes the importance of diet, lifestyle, and environmental conditions in maintaining health. This empirical, patient-centered approach marked an important shift towards scientific reasoning in medicine. Democritus, another pre-Socratic thinker, introduced the concept of the atom, an indivisible unit of matter. Although his atomic theory lacked experimental support at the time, his idea that everything is composed of small, invisible particles interacting in a void was remarkably prescient. It would take over 2,000 years for atomic theory to be confirmed through modern science. But the conceptual leap made by Democritus remains one of the most striking achievements of early natural philosophy. Socrates, while not a scientist in the traditional sense, influenced the development of scientific thought through his method of questioning and dialogue. He emphasized the importance of critical thinking, ethical inquiry, and the search for definitions. His student, Plato, extended these ideas into a broader metaphysical system. Plato believed that true knowledge resided in the world of ideal forms, perfect, unchanging realities that could only be grasped through reason. While this emphasis on abstract reasoning sometimes distanced Plato from empirical science, his focus on deductive logic and idealized models influenced the development of mathematics and theoretical science. Aristotle, Plato's student, brought many of these threads together into a comprehensive system of natural philosophy. He was perhaps the first to attempt a complete explanation of the natural world based on observation, classification, and logical analysis. Aristotle's writings covered a vast range of topics: physics, biology, metaphysics, ethics, logic, and more. In biology, he conducted systematic studies of animals, classifying them by anatomy, behavior, and habitat. In doing so, he laid the foundations for the science of zoology. Aristotle's method combined observation with theoretical reasoning. He believed that everything in nature had a purpose, telos, and that understanding an object required knowing both its material causes and its final purpose. While some of his theories, such as the geocentric model of the universe or the idea that heavier objects fall faster than lighter ones, were later disproven, his commitment to empirical observation and systematic classification influenced scientific thinking for centuries. Aristotle also developed formal logic, particularly the syllogism, as a method for deducing conclusions from premises. This system of reasoning became the standard for scientific and philosophical thought in the Western world for more than a millennium. While modern science eventually moved beyond some of Aristotle's assumptions, his emphasis on observation, categorization, and logical consistency remained central. During the Hellenistic period that followed Alexander the Great's conquests, Greek scientific knowledge expanded and became more specialized. In cities such as Alexandria, scholars had access to vast libraries and laboratories where they could conduct research and share findings. Euclid, working in Alexandria around 300 BCE, compiled and systematized Greek geometry in his work Elements, which became one of the most influential textbooks in history. Archimedes, another towering figure of the Hellenistic age, made significant contributions to mathematics, physics, and engineering. He developed principles of leverage, buoyancy, and calculated the value of pi with remarkable accuracy. In astronomy, the Greek scholar Aristarchus of Samos proposed a heliocentric model of the solar system, suggesting that the Earth revolved around the Sun. While his ideas were not widely accepted at the time, they demonstrated the willingness of Greek thinkers to challenge traditional assumptions based on rational analysis and observation. Hipparchus and later Ptolemy developed detailed astronomical models, with Ptolemy's Almagest becoming the authoritative text on celestial mechanics for over 1,000 years. The contributions of Greek thinkers to science were not limited to content. They also advanced the methods by which science operates. Their emphasis on logical reasoning, empirical observation, and theoretical modeling provided a template for later scientific endeavors. Even as many of their conclusions were revised or rejected, the intellectual framework they established continued to shape how people approached the study of nature. In summary, Greek philosophy laid the intellectual foundation for modern science by introducing critical methods of reasoning, emphasizing rational explanations for natural phenomena, and seeking universal principles behind observable events. While rooted in philosophical inquiry, Greek thought gradually developed toward more empirical and systematic forms of investigation. The transition from myth to reason, from anecdote to evidence, and from isolated facts to theoretical systems marks a crucial phase in the history of science. The legacy of Greek thinkers is evident not only in what they discovered, but in how they taught future generations to discover. The period often referred to as the Middle Ages, spanning roughly from the 5th to the 15th century, has long been misunderstood in the history of science. It is sometimes portrayed as a time of intellectual stagnation, where scientific progress came to a halt under the weight of dogma, superstition, and religious control. However, this simplistic view overlooks the complexity of the period and the many contributions that were made, particularly in preserving, transmitting, and even advancing knowledge. Rather than a dark void between the glories of antiquity and the scientific revolution, the Middle Ages played a crucial role in shaping the foundations of modern science. The early part of the Middle Ages, especially in Western Europe after the fall of the Roman Empire, was marked by political instability and fragmentation. Many classical texts were lost or neglected, and the infrastructure that had supported scholarship, libraries, schools, institutions, was significantly diminished. In this context, the role of the Christian Church became central, both as a preserver of knowledge and as a gatekeeper. Monasteries and cathedral schools became centers of learning, where clerics copied ancient manuscripts and studied Latin texts, primarily for theological purposes. The dominant intellectual framework during this time was scholasticism, a method of learning that emphasized the analysis of classical texts through logical reasoning. It was particularly focused on harmonizing Christian doctrine with the works of ancient authors, especially Aristotle. Although often criticized for its rigidity and reliance on authority, scholasticism introduced important tools for analysis and debate. Scholars like Thomas Aquinas, Albertus Magnus, and Duns Scotus developed sophisticated systems of logic and inquiry that would influence later thinkers. Aquinas, for example, attempted to reconcile Christian theology with Aristotelian natural philosophy. His synthesis, known as Thomism, provided a structure in which reason and faith could coexist. He argued that truths discovered through reason and those revealed through divine revelation could not contradict each other, as both ultimately came from the same source. This approach, while theological in motivation, reinforced the idea that the natural world could and should be studied through reasoned investigation. While Western Europe struggled to maintain its intellectual heritage during the early Middle Ages, significant advances were taking place elsewhere, particularly in the Islamic world. Between the 8th and 13th centuries, a flourishing of scientific activity occurred in regions stretching from Spain and North Africa to Persia and India. This period, often called the Islamic Golden Age, produced remarkable achievements in mathematics, astronomy, medicine, chemistry, and philosophy. One of the most important contributions of Islamic scholars was the preservation and translation of Greek texts. In centers like Baghdad's House of Wisdom, scholars translated the works of Aristotle, Galen, Ptolemy, Euclid, and others into Arabic. These texts were not merely preserved. They were critically analyzed, commented upon, and expanded. Thinkers such as Al-Farabi, Avicenna, Ibn Sina, and Averroes, Ibn Rushd, engaged deeply with Greek philosophy and made original contributions of their own. Avicenna's Canon of Medicine, for example, was a comprehensive medical encyclopedia that combined classical knowledge with clinical observations. It remained a standard reference in both the Islamic world and Europe for centuries. Al-Hazan ibn al-Haytham, a pioneer in optics and experimental physics, emphasized the importance of empirical observation and experimentation. His workbook of optics described the scientific method in ways that would later resonate with European scholars during the Renaissance. In mathematics, scholars such as Al-Khwarizmi made foundational contributions to algebra, a term derived from the title of his book Al-Kitab al-Mukhtasar, Fi Hizb al-Jabr wal-Muqabala, introduced Hindu-Arabic numerals, and developed algorithms, the very term derived from his name. These mathematical tools would later become indispensable to the development of physics and engineering in Europe. The interaction between the Islamic and European worlds intensified during the 11th and 12th centuries, particularly through contact in Spain and Sicily. European scholars began translating Arabic texts, which often included earlier Greek works, into Latin. This intellectual revival, known as the 12th century Renaissance, reintroduced much of classical science and philosophy to Western Europe, now filtered through the lens of Islamic scholarship. Figures like Gerard of Cremona, Adelard of Bath, and Michael Scott played crucial roles in this translation movement. With the return of Aristotle's complete works to Europe, scholastic scholars gained access to a more comprehensive natural philosophy. Universities began to form, with institutions like the University of Paris, Oxford, and Bologna becoming centers of study not only in theology and law, but also in logic, medicine, and natural philosophy. The university model provided a structured environment for scholarly debate and transmission of knowledge, laying the groundwork for scientific institutions to come. Despite these developments, science in the medieval European context was still largely subordinate to theology. Natural inquiry was permitted, even encouraged, so long as it did not contradict church doctrine. However, this did not prevent the emergence of new ideas. For example, Roger Bacon, a Franciscan friar and scholar, emphasized the importance of empirical methods and argued that knowledge should be based on experience and experimentation. He studied optics, astronomy, and alchemy, and called for the reform of scientific education. Though often viewed as a solitary visionary, Bacon's work reflected broader currents of thought developing within medieval scholasticism. Another significant figure was Jean Buridan, who challenged Aristotelian physics by proposing the concept of impetus, a precursor to the modern understanding of inertia. Similarly, Nicole Oersma questioned the geocentric model of the universe and suggested that Earth's rotation could explain celestial motion, ideas that anticipated Copernican theory. While these proposals did not yet constitute a full scientific revolution, they demonstrate that medieval scholars were actively questioning established authorities and exploring alternative models. It is also worth noting the development of technologies during this period, which had indirect but significant effects on scientific progress. The invention of the mechanical clock, the development of eyeglasses, improvements in agricultural tools, and advancements in architecture, e.g., Gothic cathedrals, all reflected growing practical knowledge and technical skill. These innovations, though not always labeled as science, contributed to the accumulation of empirical experience and problem-solving techniques that would inform later scientific methodology. By the end of the Middle Ages, the intellectual landscape of Europe had changed significantly. A foundation had been laid for the transition to the Renaissance and the scientific revolution. While theological frameworks still shaped much of academic life, the tools for independent inquiry, logic, mathematics, observation, experimentation had become more widespread. Knowledge was increasingly organized, preserved, and transmitted through institutions that could support sustained research. In conclusion, the Middle Ages should not be seen as a hiatus in scientific development, but rather as a period of transition and preparation. The preservation and transformation of ancient knowledge, the development of educational institutions, the influence of Islamic scholarship, and the slow but steady growth of empirical reasoning all contributed to the conditions necessary for science to flourish in the modern era. Far from being a step backward, the Middle Ages provided the intellectual and institutional groundwork upon which the future of science would be built. The period between the 16th and 17th centuries witnessed one of the most significant transformations in human thought, the scientific revolution. This era saw a fundamental shift in how people understood the natural world. No longer content to accept knowledge based solely on ancient authority or philosophical speculation, Thinkers of the scientific revolution increasingly relied on observation, experimentation, mathematical reasoning, and empirical evidence. It was a decisive moment that laid the foundation for modern science and redefined humanity's relationship with nature. The revolution did not happen overnight. Rather, it was the result of centuries of accumulated knowledge, intellectual debate, and the gradual erosion of old frameworks. By the time of the Renaissance, European scholars had access to a wealth of classical texts, advanced mathematics from the Islamic world, and new technological tools such as the printing press and improved navigational instruments. These developments, combined with a renewed interest in the natural world, created a fertile ground for new ways of thinking. One of the most iconic moments that symbolizes the beginning of the scientific revolution was the publication of De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres, by Nicholas Copernicus in 1543. In this work, Copernicus proposed a heliocentric model of the universe, in which the Earth and other planets revolve around the Sun. This theory stood in stark contrast to the long-standing geocentric model of Ptolemy, which had been accepted for over 1,000 years and was deeply embedded in both scientific and religious thought. Copernicus' heliocentric theory was not immediately embraced. In fact, it faced resistance from scholars and clerics alike. But it challenged the very structure of the cosmos as it had been understood and laid the foundation for more accurate astronomical observations and theories. Importantly, Copernicus' work also reintroduced the idea that scientific models could be mathematical constructs used to predict phenomena rather than literal representations of physical reality, a subtle but profound shift in scientific thinking. Following Copernicus, Tycho Brahe, a Danish astronomer, made extensive observations of the heavens, meticulously recording the positions of stars and planets without the aid of a telescope. His data would later prove instrumental for Johannes Kepler, who used it to develop his 3 laws of planetary motion. Kepler's work marked a turning point in astronomy, as it replaced the idea of circular orbits with elliptical ones and established precise mathematical relationships describing planetary movement. Kepler's laws demonstrated that the heavens followed discoverable, consistent rules, a concept that was both revolutionary and empowering for future scientists. Another transformative figure was Galileo Galilei. Often considered one of the fathers of modern science, Galileo combined observation, experimentation, and mathematical analysis in ways that became a model for future scientific inquiry. With the newly invented telescope, Galileo observed the moons of Jupiter, the phases of Venus, the rough surface of the moon, and countless new stars, discoveries that directly contradicted the Aristotelian cosmology and supported the Copernican model. Galileo also conducted experiments on motion, challenging the long-held Aristotelian belief that heavier objects fall faster than lighter ones. Through inclined plane experiments, he showed that objects accelerate uniformly under gravity, laying the groundwork for classical mechanics. His insistence on empirical evidence and his ability to communicate complex ideas clearly made him a powerful figure in the scientific world, and a controversial one in the religious and political domains. His eventual trial and condemnation by the Inquisition in 1633 demonstrated the tensions between new science and traditional authority. While Galileo was experimenting with motion and Kepler was reformulating planetary paths, another figure was preparing to unify these separate discoveries into a coherent system. That figure was Isaac Newton. In 1687, Newton published Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, often simply called the Principia. In this monumental work, Newton formulated the laws of motion and universal gravitation, providing a unified framework that explained both terrestrial and celestial mechanics. Newton's laws showed that the same forces that governed the fall of an apple on Earth also dictated the movement of the moon and planets. This universal applicability of physical laws was a breakthrough that transformed the scientific worldview. Moreover, Newton's use of mathematics, particularly calculus, which he co-developed independently of Leibniz, demonstrated the power of mathematical reasoning to describe nature with precision. The scientific revolution was not limited to astronomy and physics. In biology and anatomy, significant advances were made as well. Andreas Vesalius, in his work De Humani Corporis Fabrica, on the fabric of the human body, challenged centuries of anatomical knowledge based on Galen, a Roman physician whose work had dominated for over a millennium. By conducting dissections and emphasizing direct observation of the human body, Vesalius established a new standard for anatomical science. In the realm of chemistry, the transition from alchemy to a more systematic and empirical discipline began to take shape. Robert Boyle, sometimes called the father of modern chemistry, rejected the mystical elements of alchemy and emphasized controlled experimentation. His work, The Skeptical Chemist, 1661, argued for a corpuscular theory of matter and laid out principles that would influence future chemical research. Boyle's law, describing the inverse relationship between the pressure and volume of a gas, is still taught today as a foundational concept in physics and chemistry. The scientific revolution also saw significant developments in methodology. Francis Bacon, in his Novum Organum, advocated for a new approach to knowledge based on inductive reasoning and systematic observation. He criticized reliance on ancient texts and emphasized the importance of accumulating data, forming hypotheses, and testing them through controlled experiments. Bacon's empirical method was influential in shaping the philosophy of science and provided a counterbalance to the more deductive, rationalist approach championed by thinkers like René Descartes. Descartes, for his part, sought to build knowledge on a foundation of absolute certainty. His famous dictum, cogito, ergo sum, I think, therefore I am, was the starting point for a philosophy based on clear and distinct ideas derived through reason. Descartes applied his rationalist method to both mathematics and natural philosophy, and his mechanistic view of the universe as a machine governed by laws complemented the emerging scientific paradigm. Another key aspect of the scientific revolution was the rise of scientific societies and institutions. The Royal Society in England, founded in 1660, and the Académie des Sciences in France, founded in 1666, provided platforms for scientists to share ideas, publish results, and establish standards for research. These institutions promoted a culture of collaboration, transparency, and skepticism, all hallmarks of modern science. The printing press also played a vital role in the spread of new scientific ideas. Books, pamphlets, and journals allowed discoveries to be disseminated widely and debated critically. The increasing literacy and availability of texts meant that scientific knowledge was no longer confined to a small elite, but became part of a growing public discourse. In summary, the scientific revolution represented a profound transformation in the way humans sought to understand the natural world. It marked the transition from reliance on authority and tradition to a method of inquiry based on observation, experimentation, and mathematical reasoning. Figures like Copernicus, Galileo, Kepler, Newton, Bacon, and Descartes reshaped the intellectual landscape, introducing new models of the universe, new methods of investigation, and a new confidence in human reason. The scientists of this era may not have fully realized they were creating a new kind of knowledge system, a formal, institutionalized science that would grow into the dominant intellectual force of the modern world. But they knew they were challenging old ideas and seeking truth through new means. Their legacy is not just in the discoveries they made, but in the methods they pioneered, methods that continue to define science to this day. As the scientific revolution gave way to the Enlightenment and the early modern period advanced, science began to undergo a structural transformation. What had previously been a relatively unified pursuit of natural philosophy began to fragment and specialize into separate fields of inquiry. This development, the birth of scientific disciplines, was not merely a matter of convenience or nomenclature. It was a profound reorganization of human knowledge, fundamentally altering how research was conducted, how expertise was defined, and how scientific institutions functioned. The emergence of distinct disciplines such as physics, chemistry, biology, and astronomy marked a turning point in the evolution of science, signifying its maturity and expansion. In antiquity and the medieval period, scholars like Aristotle or Galen were generalists. They explored the natural world in its entirety, without the constraints of disciplinary boundaries. A single thinker could write about biology, ethics, astronomy, and politics within the same corpus. During the Renaissance and even the early stages of the scientific revolution, this holistic approach persisted. Leonardo da Vinci studied human anatomy alongside mechanics and hydraulics. Galileo Galilei investigated motion, optics, and astronomy. But as knowledge expanded, so did the need to organize it. The specialization of science was both a response to and a product of increased empirical discovery. As observations grew more precise and instruments more refined, questions became more detailed and complex. No single individual could master all branches of inquiry. The volume of data being produced demanded categorization, and researchers began to focus more narrowly, often mastering one small domain at the expense of broader knowledge. One of the earliest and clearest examples of disciplinary separation occurred between physics and chemistry. During the 17th century, natural philosophers explored questions about matter, motion, and transformation using a mixture of experimental techniques and speculative thought. But by the 18th century, these inquiries began to split. Physics became associated with mechanics, thermodynamics, optics, and electromagnetism, phenomena that could be expressed mathematically and described through laws. Chemistry, by contrast, focused on the composition of substances, reactions, and transformations at the material level. Chemistry's emergence as a distinct science is closely associated with Antoine Lavoisier, who in the late 18th century redefined the field with his quantitative experiments. By introducing the concept of conservation of mass and developing a systematic nomenclature for chemical substances, Lavoisier laid the foundation for modern chemistry. His work helped distinguish chemistry from alchemy, transforming it from a speculative practice into an empirical, experimentally grounded science. At the same time, biology began to coalesce into its own field. While the study of living organisms had always been part of natural philosophy, it was often fragmented across anatomy, botany, and medicine. The invention of the microscope in the 17th century revealed a previously invisible world: cells, microorganisms, tissue structures that demanded new frameworks of understanding. Thinkers like Robert Hooke and Antony van Leeuwenhoek opened up an entirely new dimension of life sciences. Their discoveries would eventually lead to the development of cell theory, microbiology, and histology. Botany and zoology, too, evolved into formal disciplines during this period. Carl Linnaeus, with his Systema Naturae, 1735, introduced a standardized method for classifying organisms, known as binomial nomenclature. His taxonomic system not only brought order to the study of living things, but also signaled biology's growing independence from general natural philosophy. Linnaeus's influence was profound, setting a precedent for empirical observation and classification that would shape biology for centuries. Astronomy, once closely tied to astrology and theology, also professionalized and specialized. Advances in telescopic technology, mathematical modeling, and observational techniques allowed astronomers to make increasingly accurate predictions and discoveries. By the 18th and 19th centuries, astronomy had become a rigorous discipline, distinct from philosophical speculation and religious interpretation. The work of astronomers like William Herschel, who discovered Uranus and cataloged nebulae, and later, Edwin Hubble, who demonstrated the expansion of the universe, shows how the field had evolved into a data-driven and mathematically intensive science. Geology and the earth sciences began to take shape in the late 18th century as well. James Hutton's theory of uniformitarianism, the idea that geological processes observed in the present have been shaping the earth for vast periods, challenged prevailing views of a young Earth shaped by catastrophic events. Charles Lyell further developed these ideas and principles of geology, arguing that slow, gradual processes like erosion and sedimentation could explain Earth's features. This perspective laid the foundation for understanding Earth's history, fossil records, and eventually, evolutionary biology. The rise of disciplines was also tied to the development of universities and research institutions. In earlier centuries, universities had focused primarily on theology, law, and medicine. But by the 18th and 19th centuries, scientific departments began to appear. Chairs of physics, chemistry, botany, and anatomy were established. These positions formalized the boundaries between subjects and created distinct communities of researchers, each with their own methods, terminologies, and goals. Institutional specialization was mirrored in scientific journals and societies. The Philosophical Transactions of the Royal Society, established in 1665, was one of the first scientific journals. Over time, as disciplines grew, more specialized publications emerged, journals of chemistry, physics, biology, medicine, and eventually subfields like neurobiology, astrophysics, and organic chemistry. These journals not only facilitated communication within disciplines, but also reinforced their boundaries. One important consequence of disciplinary emergence was the increasing role of professional identity. Scientists began to define themselves by their field. One was no longer simply a natural philosopher, but a chemist, a physicist, a geologist. This shift affected education, careers, and the structure of scientific authority. Expertise became more narrowly defined, and specialization often became a requirement for credibility. While the formation of disciplines brought many benefits, allowing for depth, rigor, and systematic inquiry, it also introduced new challenges. Interdisciplinary communication became more difficult. Researchers in different fields developed unique terminologies and methodologies, sometimes struggling to collaborate or understand each other's work. This fragmentation occasionally led to isolation, where crucial insights in one field were overlooked in another. Despite these challenges, the structure of disciplines proved resilient. Over time, even more specialized subfields emerged. Physics, for example, split into classical mechanics, electromagnetism, thermodynamics, quantum physics, and relativity. Chemistry branched into organic, inorganic, physical, and analytical chemistry. Biology expanded into genetics, molecular biology, ecology, and evolutionary biology. Each subfield developed its own techniques, instruments, and theories. Yet even as disciplines grew more distinct, they remained interconnected. Breakthroughs in one area often relied on techniques or principles from another. The discovery of DNA's double helix, for instance, involved X-ray crystallography, a method from physics, chemical analysis of nucleotides, and biological insights into heredity. This highlights the paradox of scientific specialization. While it fosters expertise and depth, it also necessitates collaboration and integration. In the modern era, this tension has given rise to interdisciplinary and transdisciplinary research. Fields like biochemistry, environmental science, cognitive science, and materials science emerge at the intersections of older disciplines. These hybrid fields remind us that the boundaries between disciplines, though useful, are human constructs, tools for managing knowledge, not absolute divisions in nature. In conclusion, the birth of scientific disciplines marked a critical phase in the evolution of science. It enabled deeper inquiry, fostered professional communities, and allowed for rapid expansion of knowledge. Though it introduced new complexities and challenges, this structuring of knowledge proved essential for the development of science as we know it. From generalists to specialists, from broad inquiry to focused research, this transformation reflects not just the growth of knowledge, but the ways in which humanity organizes its quest to understand the universe. The 18th century, often called the Age of Enlightenment, marked a pivotal moment in the history of science, not only in the production of knowledge, but in the very way scientific knowledge was perceived, structured, and disseminated. This period saw science become increasingly institutionalized, professionalized, and embedded within society's broader intellectual, cultural, and political fabric. During the Enlightenment, science stepped out of the confines of private study and into public life, becoming an essential part of human progress and a central force in reshaping the modern world. The Enlightenment was an intellectual movement grounded in the belief that reason, observation, and rational thought could be used to improve society and liberate humanity from ignorance, superstition, and tyranny. Thinkers of this era emphasized education, skepticism toward authority, and the power of empirical knowledge. Science was no longer viewed simply as a tool to understand the natural world. It was increasingly seen as a vehicle for social reform, economic development, and moral enlightenment. One of the most significant developments of this period was the establishment and expansion of scientific institutions. Royal academies, scientific societies, universities, and journals flourished across Europe. These institutions formalized scientific inquiry, provided platforms for communication and peer review, and helped create a culture of organized, methodical research. While the seeds of these institutions were planted during the scientific revolution, it was during the Enlightenment that they became truly central to scientific life. The Royal Society in England, founded in 1660, and the Académie des Sciences in France, established in 1666, continued to grow in prominence. Other countries followed suit. The Berlin Academy, 1700, the St. Petersburg Academy, 1724, and the Royal Swedish Academy of Sciences, 1739, among others. These institutions were often supported by monarchs or governments who recognized the strategic value of scientific advancement for military innovation, navigation, agriculture, and economic growth. Crucially, these academies promoted the idea that science should serve the public good. They supported applied science, sponsored expeditions, advised governments, and worked to spread scientific literacy. This signaled a shift from the solitary scholar or gentleman natural philosopher toward a collective, institutional model of scientific progress. Scientific academies also helped define what counted as legitimate science, creating standards for evidence, methodology, and publication. The emergence of scientific journals further accelerated this institutionalization. Before the Enlightenment, most scientific communication occurred through private correspondence or unpublished manuscripts. But with the rise of journals like Philosophical Transactions and Memoires de l'Académie des Sciences, a new model of knowledge sharing was born. These publications allowed scientists to disseminate findings, build on each other's work, and engage in debate. Peer review gradually became a norm, reinforcing quality and accountability. Universities also began to adapt to the growing importance of science. While many institutions were still rooted in medieval curricula based on theology, law, and the classics, the The 18th century saw the gradual incorporation of scientific subjects. Mathematics, physics, chemistry, anatomy, and natural history became part of formal education. Chairs in scientific disciplines were established, and laboratories began to appear on university campuses. Though full modernization of the university system would come later, in the 19th century, this period laid the groundwork. Public engagement with science grew dramatically during the Enlightenment. Scientific lectures, demonstrations, and exhibitions became popular in urban centers. Wealthy patrons and curious citizens attended events where electricity, magnetism, optics, and chemical reactions were demonstrated with theatrical flair. These spectacles were not mere entertainment. They reflected a cultural shift. Science was no longer the domain of cloistered elites. It was becoming a shared pursuit, one that promised both wonder and utility. The rise of the popularizer, or scientific communicator, also became important. Figures like Joseph Priestley, Benjamin Franklin, and Voltaire wrote extensively about scientific topics for general audiences. Their writings blended explanation with advocacy, encouraging the public to embrace science as a rational, enlightening force. Books such as Priestley's The History and Present State of Electricity, 1767, or Franklin's Letters on Electricity helped translate complex concepts into accessible language. Voltaire's embrace of Newtonian science was especially influential in France. His Elements of the Philosophy of Newton helped introduce Newton's ideas to a broader European audience, countering the still dominant Cartesian philosophy in French intellectual circles. Enlightenment thinkers increasingly saw science as the backbone of rational thought, an exemplar of how clear evidence and logical reasoning could overcome dogma and confusion. The Enlightenment also contributed to the shaping of science as a profession. Previously, science was often pursued by aristocrats, clergy, or independently wealthy individuals with the time and resources to conduct experiments. But the rise of formal institutions, teaching roles, and state-sponsored research created new career paths. Scientific expertise began to carry social prestige, and credentials increasingly mattered. While the full transformation into modern scientific professions would occur in the 19th century, the Enlightenment sowed the seeds for this shift. Importantly, Enlightenment science was not confined to Europe. Exploratory expeditions spread scientific knowledge around the globe, and colonial powers used scientific practices as tools of empire. Botanical gardens, observatories, and natural history museums were established in colonized regions, often staffed by European scientists or local collaborators trained in Western methods. These practices helped build global networks of scientific exchange, but also reinforced asymmetrical power dynamics, with European institutions often claiming authority over knowledge production. One major Enlightenment figure who embodied the spirit of institutional science was Antoine Lavoisier. His work in chemistry, conducted at the French Academy of Sciences, established principles such as the conservation of mass and the role of oxygen in combustion. Lavoisier also emphasized careful measurement and reproducibility, aligning with the Academy's broader goals of standardization and rigor. His tragic execution during the French Revolution reminds us that even the most rational enterprises are not immune to political turmoil. The Enlightenment also nurtured philosophical reflections on science. Thinkers such as Immanuel Kant and David Hume explored the foundations of human knowledge, questioning how we know what we know. Kant's critique of pure reason examined the limits of empirical inquiry, while Hume's skepticism about causality posed deep challenges to scientific assumptions. These debates did not undermine science. Rather, they enriched it by forcing greater introspection about its assumptions, methods, and implications. Another legacy of the Enlightenment was the growing belief in progress. Science was increasingly seen as cumulative and directional. each generation building on the last, each discovery bringing humanity closer to truth and improvement. This optimism, though sometimes naive, fueled investments in education, infrastructure, and public health. The Enlightenment belief in rational improvement would continue to shape scientific culture into the modern era. Still, Enlightenment science had its limits. It remained largely dominated by elite men in Europe, with women, the poor, and non-Europeans largely excluded from formal institutions. Though some women, like Emily du Châtelet, who translated Newton's Principia into French, made significant contributions, systemic barriers remained. Efforts to democratize science through public lectures and books were a start, but full inclusion would take centuries. In summary, the Enlightenment was a transformative period in the history of science. It witnessed the institutionalization of scientific research through academies, journals, and universities. It expanded public engagement and made science a cultural force. It laid the intellectual and infrastructural foundations for the scientific professions and for the concept of science as a rational, evidence-based method for understanding and improving the world. While not without contradictions and exclusions, the Enlightenment marked science's full emergence as a central pillar of modern thought and society. The 19th century marks one of the most decisive turning points in the history of science. While the Enlightenment laid the foundations for institutionalizing and democratizing science, it was in the 1800s that science experienced its massive internal expansion. During this time, scientific activity became more deeply professionalized, technical, and compartmentalized. The figure of the gentleman philosopher gave way to that of the career scientist. Entirely new disciplines emerged, and the boundaries between them began to solidify. In short, the 19th century witnessed the definitive fragmentation of science into specialized branches, each with its own methods, goals, institutions, and identities. By the beginning of the 1800s, the volume of knowledge in the sciences had grown to such an extent that no individual could hope to master even a fraction of it. In the 17th and 18th centuries, it was still plausible for a figure like Isaac Newton or Carl Linnaeus to contribute meaningfully to multiple areas of inquiry. By contrast, in the 19th century, the rapid accumulation of experimental results, theoretical developments, and technological tools made generalist knowledge increasingly obsolete. This drove scientists to narrow their focus and develop distinct communities of practice. In effect, science no longer operated as a single endeavor. It became a vast network of increasingly autonomous disciplines. This specialization was both cause and consequence of a series of transformations in higher education and scientific infrastructure. Universities began to redefine themselves not merely as institutions of moral and philosophical instruction, but as research centers. Nowhere was this more evident than in Germany, where the so-called Humboldtian model, named after Wilhelm von Humboldt, revolutionized academic life. German universities emphasized the unity of teaching and research, the cultivation of academic freedom, and the production of new knowledge through systematic investigation. Professors were not simply transmitters of received wisdom. They were expected to be active researchers at the frontiers of their respective fields. This model spread throughout Europe and into the United States, most notably influencing the development of research institutions such as Johns Hopkins University, founded in 1876, which was explicitly modeled on German universities. As a result, the 19th century saw an enormous expansion of academic departments and the establishment of new chairs in fields like organic chemistry, geology, physiology, and experimental physics. Each discipline developed its own professional norms, degree programs, and educational pathways. Simultaneously, scientific societies and conferences multiplied. The British Association for the Advancement of Science, founded in 1831, the the American Association for the Advancement of Science, 1848, and many national chemical, physical, and biological societies formed to support specialized communities. These organizations offered venues for discussion, recognition, and dissemination of work, allowing researchers to communicate more effectively within their increasingly narrow fields. Journals, too, became more specialized. The generalist journals of earlier centuries gave way to more focused publications like Annalen der Physik, the Journal of the Chemical Society, and Proceedings of the Linnean Society. This process not only reflected the internal diversification of science, but also reinforced it. Specialized journals created feedback loops in which researchers published, read, and reviewed within tightly defined boundaries, strengthening the identity and autonomy of each field. The rise of chemistry as a distinct and central science during this period illustrates these broader trends. The development of organic chemistry, for instance, transformed how scientists understood the material world. Friedrich Wöhler's synthesis of urea in 1828 demonstrated that organic substances could be produced from inorganic materials, challenging the long-held idea of a vital force unique to living organisms. Chemists such as Justus von Liebig, August Kekule, and Dmitry Mendeleev advanced the discipline through foundational work on chemical structure, reaction mechanisms, and the periodic table of elements. Their efforts not only deepened the understanding of chemical processes, but also shaped how chemistry was taught and practiced. Similarly, physics underwent major transformations. The field moved beyond Newtonian mechanics into new territories, including electromagnetism, thermodynamics, and eventually statistical mechanics. James Clerk Maxwell's equations unified electricity and magnetism into a coherent theoretical framework, laying the groundwork for electromagnetic theory. Simultaneously, Rudolf Clausius and Lord Kelvin helped establish thermodynamics, a field with profound implications for understanding energy, heat, and entropy. These breakthroughs were deeply mathematical and theoretical, and they contributed to the growing image of physics as the most precise and fundamental of the sciences. Biology, too, was undergoing a revolution. Perhaps the most dramatic moment came in 1859 with the publication of Charles Darwin's On the Origin of Species. Darwin's theory of natural selection provided a unifying explanation for the diversity of life and placed biology on a firmer theoretical foundation. In parallel, the study of anatomy, embryology, taxonomy, and physiology continued to expand. The cell theory, developed by Matthias Schleiden and Theodor Schwann, established the cell as the basic unit of life. Gregor Mendel's work on inheritance, though largely ignored in his lifetime, would later become the cornerstone of genetics. Increasingly, biology was recognized not as a descriptive science, but as one driven by underlying laws and mechanisms, much like physics and chemistry. Another major development was the emergence of the earth sciences as distinct fields. Geology matured through the work of Charles Lyell, who popularized the idea that Earth's features were shaped by slow, continuous processes over long timescales. This principle, known as uniformitarianism, provided a framework for interpreting Earth's past and had significant implications for evolutionary theory. Paleontology, mineralogy, and geography also grew as independent disciplines, each with its own empirical methods and classification systems. Mathematics, long a central tool for other sciences, also began to take on a more abstract and autonomous role in the 19th century. Fields such as algebra, number theory, topology, and mathematical logic expanded rapidly. Mathematicians like Gauss, Riemann, and Cantor not only advanced theoretical mathematics, but also contributed to the conceptual tools used by physicists and engineers. The line between pure and applied mathematics became more clearly delineated, reflecting the broader trend of specialization. Perhaps the most telling indicator of specialization was the changing identity of the scientist. In the early part of the century, the term scientist itself was not in common use. It was coined only in 1833 by William Wool. Prior to that, individuals engaged in scientific work were known as natural philosophers, chemists, physicians, or engineers. But as science professionalized, a new identity emerged. This scientist was someone whose career, training, and daily activity were defined by rigorous empirical inquiry, usually within a defined discipline. With this identity came a new set of values and expectations. Scientists were now expected to produce original research, publish in peer-reviewed journals, attend conferences, and contribute to their professional community. The amateur scientists still existed, especially in fields like natural history or astronomy, but the center of gravity had shifted. Science was becoming a career, not just a calling. Despite the many advantages of specialization, it also brought challenges. Communication between disciplines became more difficult, and fragmentation sometimes led to intellectual silos. The richness of cross-disciplinary thought that had characterized earlier eras was harder to maintain in an age of deep specialization. Even within a single field, subfields multiplied. For example, physics eventually split into experimental and theoretical branches, each with its own techniques, training, and philosophical outlook. Nonetheless, the specialization of science in the 19th century laid the groundwork for the enormous advances of the 20th. By carving out distinct areas of expertise, science became more capable of tackling complex problems in a systematic and scalable way. Laboratories grew in scale and ambition. Funding for scientific research, both public and private, increased. And most importantly, society began to see science not just as a source of abstract knowledge, but as an engine of innovation, industry, and social transformation. In summary, the 19th century witnessed the transformation of science from a relatively unified intellectual enterprise into a structured system of distinct disciplines. This development was driven by the explosion of knowledge, the rise of research universities and scientific societies, and the professionalization of scientific careers. Specialization brought precision, depth, and clarity, even as it created new challenges for integration and communication. It marked the transition into the modern era of science, complex, compartmentalized, but undeniably powerful. The 20th century ushered in an era in which science became not only a powerful intellectual force, but a central institution of modern society. No longer confined to universities, laboratories, or elite academies, science began to integrate into governments, industries, military establishments, public health systems, and even popular culture. The scale of scientific research expanded dramatically, often funded by states and corporations, and the consequences of scientific discovery became inseparable from the political, ethical, and social dimensions of human life. Science was now a collective endeavor with societal reach, and with that reach came unprecedented responsibility, scrutiny, and influence. At the dawn of the century, scientific optimism was soaring. Advances in electricity, magnetism, chemistry, and engineering had already revolutionized daily life in the 19th century, and many believed that science would continue to lead humanity toward progress, reason, and prosperity. This belief was reinforced by early breakthroughs in areas like relativity and quantum mechanics, fields that transformed our understanding of nature at both cosmic and microscopic levels. The work of Albert Einstein, Niels Bohr, Werner Heisenberg, and others not only pushed physics into new conceptual terrain, but also captivated the public imagination. The universe, it seemed, was becoming knowable in entirely new ways. At the same time, science began to receive large-scale, systematic funding, particularly in industrialized countries. governments and private industries realized the economic and strategic value of research and development, R&D. Chemical companies invested in synthetic materials, pharmaceuticals, and agricultural science. Electrical firms supported engineering research. National academies and government research councils, like the U.S. National Research Council, founded in 1916, began coordinating scientific work at the national level. Scientists were now not just scholars, but civil servants, innovators, and consultants. This trend accelerated dramatically during the two world wars, particularly World War II. Science played a pivotal role in military strategy, leading to the development of radar, sonar, antibiotics, advanced weaponry, cryptography, and, most famously, nuclear technology. The Manhattan Project, an enormous collaboration involving over 100,000 people and some of the world's top physicists, produced the first atomic bombs, which were dropped on Hiroshima and Nagasaki in 1945. This event marked a profound shift in the relationship between science and society. For the first time, scientific knowledge had led directly to the creation of a weapon of mass destruction capable of annihilating cities in seconds. The atomic bomb became a symbol of both scientific power and moral dilemma. Scientists such as Robert Oppenheimer, who had led the Manhattan Project, publicly wrestled with the ethical implications of their work. The post-war period saw increasing awareness that science was no longer a purely academic or idealistic pursuit. It could serve human welfare or contribute to catastrophic violence. As a result, many scientists began to advocate for public dialogue about the uses and limits of scientific knowledge. This was also the era in which the term big science entered the lexicon. The scale of scientific research, especially in physics and biology, grew immensely, characterized by large teams, multi-million-dollar budgets, massive facilities, and collaborations between academia, government, and industry. Projects like CERN's particle accelerators or NASA's space programs required decades of planning, thousands of researchers, and international cooperation. Science had become an institution with bureaucracies, hierarchies, and long-term strategic goals. Alongside the rise of big science came a deepening integration of science into national policy. During the Cold War, scientific research was seen as a cornerstone of geopolitical competition. The Soviet launch of Sputnik in 1957 triggered the space race, leading to the establishment of NASA and increased U.S. investment in science education and research. In both the United States and the Soviet Union, scientific innovation was tied to national pride and security. Governments established massive agencies, like the National Science Foundation, NSF, and the Defense Advanced Research Projects Agency, DARPA, to support research deemed strategically important. Yet even as physics and engineering were shaping geopolitics, the life sciences were undergoing a revolution of their own. The discovery of the structure of DNA by James Watson and Francis Crick in 1953, with the crucial contributions of Rosalind Franklin, transformed biology. Molecular biology, genetics, and biochemistry became dominant disciplines, leading to the rise of biotechnology in the latter part of the century. Genetic engineering, cloning, and eventually genome sequencing changed not only how scientists understood life, but how humans could intervene in its processes. Medical science also flourished, with dramatic improvements in disease prevention, diagnosis, and treatment. Vaccination campaigns nearly eradicated diseases like polio and smallpox. Antibiotics revolutionized the treatment of infections. Advances in surgery, imaging technologies, and reproductive medicine further expanded the reach of scientific knowledge into everyday life. Public health initiatives, supported by epidemiological research, helped extend life expectancy and reduce infant mortality across much of the world. However, these achievements also brought challenges. As science gained authority, It was increasingly called upon to address problems that were not only technical, but moral, environmental, and philosophical. The 20th century saw the emergence of bioethics, driven by concerns over human experimentation, reproductive technologies, and end-of-life decisions. The atrocities committed in the name of science by Nazi doctors during World War II, for example, led to the Nuremberg Code, which laid the foundation for ethical standards in human research. In parallel, environmental science emerged as a crucial field in the mid-20th century. Rachel Carson's Silent Spring, 1962, sounded the alarm on the ecological consequences of industrial chemicals like DDT, helping to launch the environmental movement. Scientists began to investigate climate change, biodiversity loss, and pollution, often facing pushback from industries and political interests. The realization that scientific and technological progress could also damage ecosystems prompted widespread public debate about sustainability, responsibility, and precaution. The second half of the 20th century also saw social sciences increasingly assert themselves. Psychology, sociology, anthropology, and economics adopted more rigorous empirical methods, seeking to be seen as sciences in their own right. The divide between the two cultures of the sciences and the humanities, famously diagnosed by C.P. Snow in 1959, became a subject of debate, but interdisciplinary initiatives began to bridge the gap. Social science research was applied to everything from education and urban planning to advertising and behavioral economics. As scientific institutions grew in power and influence, questions arose about their internal structures and the distribution of authority within them. The image of the lone genius was giving way to a more complex reality. Science was collaborative, competitive, and embedded in social systems. Feminist scholars, post-colonial critics, and historians of science began to interrogate the assumptions, exclusions, and hierarchies that shaped scientific knowledge. They showed how gender, race, and class could affect what questions were asked, who got funding, and which results were accepted. Meanwhile, public trust in science experienced both high and low points. On one hand, achievements like the moon landing, the eradication of smallpox, and the rise of the internet demonstrated science's transformative power. On the other hand, events like the Vietnam War or scientific research contributed to weapons like Agent Orange, the Challenger disaster, and the handling of the HIV/AIDS crisis exposed failures, uncertainties, and political entanglements. Debates about nuclear energy, genetic modification, and climate change further highlighted the tensions between scientific knowledge and public values. By the end of the 20th century, science was fully entrenched as a central institution in modern life, interconnected with politics, economics, education, ethics, and culture. Scientists were no longer viewed as isolated figures in ivory towers. They were policymakers, entrepreneurs, media personalities, and sometimes activists. The authority of science remained strong, but it was increasingly tempered by demands for transparency, inclusiveness, and public accountability. In essence, the 20th century saw science evolve from a relatively self-contained intellectual activity into a vast, institutionalized, and socially embedded enterprise. It became a critical actor on the global stage, capable of producing miracles and disasters, insights and dilemmas. Science shaped the world more profoundly in this century than ever before, but in doing so, it also revealed the need for reflection, dialogue, and responsibility in the pursuit of knowledge. One of the most intriguing questions in the history of science is whether scientists know they are creating a new science while they are doing it. In retrospect, it's often easy to draw clean lines. Here is where biology began, or here is the moment psychology became a science. But history rarely unfolds in such clear-cut ways. The emergence of a new scientific discipline is typically a slow, messy, and sometimes accidental process. The people involved are often more concerned with solving a specific problem, answering a curious question, or applying a method, rather than consciously constructing a new branch of knowledge. And yet, over time, those efforts often solidify into entirely new sciences. So, do scientists know they are creating a new field? Sometimes yes, often no, and in many cases, it's somewhere in between. To begin with, it's important to recognize that creating a science is not simply a matter of discovering something new. Many discoveries remain isolated until a broader framework or methodology is developed to organize and build upon them. What distinguishes a new science from a collection of interesting facts is the establishment of a coherent system, shared questions, methods, terminology, educational institutions, publications, and a community of practitioners. In other words, the creation of a science involves not just content but structure. That structure rarely appears fully formed from the outset. Take psychology, for instance. For centuries, questions about the human mind, behavior, emotion, and thought were addressed by philosophers and theologians. Plato, Aristotle, Descartes, and others speculated deeply about the soul and the nature of consciousness, but there was little empirical or systematic research. It wasn't until the late 19th century that psychology began to present itself as a distinct science. Wilhelm Wundt, often credited as the father of modern psychology, established the first experimental psychology laboratory in Leipzig in 1879. Wundt didn't just conduct experiments. He sought to define psychology as an empirical science, complete with controlled methods, repeatable observations, and a specialized vocabulary. But even Wundt may not have fully grasped the long-term significance of what he was doing. He viewed psychology as a kind of bridge between philosophy and physiology. He believed in introspection and structured experimentation, but he couldn't have predicted the diversity of schools that would soon arise: Freudian psychoanalysis, behaviorism, cognitive psychology, and beyond. What began as an attempt to bring scientific rigor to the study of mental processes eventually fragmented into subfields with their own identities and disputes. Psychology didn't arrive all at once. It evolved through internal debates, experimental innovations, and shifting cultural contexts. A similar story can be told about sociology. Auguste Comte, in the early 19th century, coined the term sociology and imagined it as the physics of society, capable of discovering laws of social behavior just as physics had uncovered laws of nature. Yet Comte's vision was more philosophical than scientific in the modern sense. It took decades, and the contributions of thinkers like Emil Durkheim, Max Weber, and Karl Marx, before sociology took shape as a discipline with empirical methods, theoretical frameworks, and university departments. Durkheim, in particular, made a deliberate effort to establish sociology as a science. He emphasized the importance of studying social facts as things, real, external, and observable patterns of behavior and thought that shape individual action. In this sense, Durkheim and others like him were very much aware that they were forging a new path. They weren't just solving problems. They were establishing the very legitimacy of a new way of understanding human life. But not all sciences begin with such intentionality. Consider cybernetics, a field that emerged in the mid-20th century around questions of control, communication, and feedback in both machines and living organisms. Norbert Wiener, who helped establish the field during and after World War II, was certainly aware that he was working on something novel. Yet cybernetics didn't neatly crystallize into a standalone science in the long run. While it had a huge influence on systems theory, artificial intelligence, neuroscience, and other areas, cybernetics itself as a discipline eventually became more of a historical curiosity. It's a powerful example of how even when scientists believe they're founding a new science, its fate depends on many factors: intellectual, institutional, and cultural. There are also examples of sciences that emerged less from conscious design and more from practical necessity. Computer science is a case in point. In the early days of computing, the work was largely done by mathematicians, engineers, and physicists. The concept of computer science as a discipline didn't exist. But as the complexity of machines and programming languages grew, a new need emerged. People had to understand how to design algorithms, manage data structures, develop software, and explore computational theory. University departments formed, textbooks were written, conferences organized, and journals established. Only then could computer science be said to truly exist, not because someone declared it so, but because it developed the self-sustaining structures of a science. One could argue that the birth of a science is similar to the formation of a language. No single person invents it from scratch. Instead, it emerges from the shared practices, needs, and innovations of a community over time. Scientists might set out to answer a question or solve a technical challenge, but in doing so, they often contribute to the creation of something larger than themselves. At the same time, it's important to acknowledge the role of institutions in defining what counts as a science. Academic departments, research funding bodies, and peer-reviewed journals all play a critical role in shaping the boundaries of scientific disciplines. In the 20th century, as universities and governments became central to the scientific enterprise, their choices about what to support, what to teach, and what to publish had enormous influence on the development of new sciences. Fields like cognitive science and neuroscience, for example, benefited greatly from interdisciplinary funding and institutional support, allowing them to grow rapidly and attract top researchers. The emergence of new technologies also drives the formation of new sciences. Advances in instrumentation, such as telescopes, microscopes, particle accelerators, and imaging technologies, often open up new domains of inquiry that eventually require new methods, theories, and institutional homes. Astrophysics, molecular biology, and nanoscience all owe much of their existence to technological breakthroughs that made previously invisible phenomena observable. Furthermore, the very concept of what constitutes a science has evolved. Historically, science was closely associated with physical phenomena and quantifiable results. But over time, the definition has broadened to include areas like behavioral economics, computational linguistics, and environmental science, fields that combine empirical rigor with interdisciplinary methods and often address complex, real-world problems. So, do scientists know they're creating a science? Sometimes they do, particularly when they are explicitly attempting to break with older traditions or forge new institutional paths. In other cases, they are simply following a problem where it leads, driven by curiosity, necessity, or opportunity. Only later does history look back and recognize the birth of a new science. In the end, the creation of a scientific discipline is as much a sociological and institutional process as it is an intellectual one. It requires not just a new idea or discovery, but a collective commitment to building a framework in which that idea can flourish. That includes communities of researchers, methods of inquiry, systems of validation, and mechanisms for education and communication. It's a complex and often unpredictable process, but one that continues to shape our understanding of the world in profound ways. Science, as powerful and transformative as it is, has boundaries. While its methodologies are remarkably effective in uncovering truths about the natural world, explaining phenomena, and predicting outcomes, science does not, and arguably cannot, answer every question or solve every problem. The notion of limits in science is not just a philosophical curiosity. It's a practical and epistemological reality that shapes how we investigate the world and how we understand the scope and responsibility of scientific inquiry. Exploring the limits of science also reveals much about its nature, its assumptions, and its relationship with other forms of knowledge such as philosophy, ethics, and art. To begin with, some limits of science are methodological. The scientific method is built upon observation, experimentation, measurement, and falsifiability. These tools are extremely effective for studying repeatable, observable phenomena under controlled conditions. But not all phenomena lend themselves to this framework. For instance, unique historical events, like the formation of a particular culture or the cause of a specific war, cannot be repeated or isolated in the way laboratory experiments can. While sciences like history, anthropology, and archaeology use rigorous methods, they must also rely on interpretation, inference, and context in ways that differ from the natural sciences. Another methodological limit concerns subjectivity and consciousness. While neuroscience and psychology have made great strides in understanding the brain and behavior, the subjective experience of consciousness, what it's like to be aware, to feel, to think, remains elusive. Known as the hard problem of consciousness, this issue highlights the difficulty of using objective tools to study inherently subjective phenomena. Can science ever fully explain qualia, the internal experiences of color, pain, joy, or memory? Many scientists and philosophers believe we are only scratching the surface, and some argue that these questions may remain forever beyond empirical explanation. Then there are limits related to uncertainty and complexity. In many areas, especially in the study of complex systems like climate, ecosystems, economies, or human societies, scientific predictions become probabilistic rather than deterministic. The more variables involved, and the more interdependent they are, the harder it becomes to predict outcomes with precision. Chaos theory and systems theory have shown that even simple systems can produce unpredictable results due to sensitivity to initial conditions. Thus, science often works within zones of uncertainty, acknowledging probabilities rather than offering certainties. Quantum mechanics presents another kind of epistemological limit. The Heisenberg uncertainty principle shows that certain pairs of physical properties, like position and momentum, cannot both be known to arbitrary precision. This is not due to faulty measurement tools, but is a fundamental feature of nature itself. At the quantum level, reality defies classical intuition, and even the act of observation can influence the outcome. These insights don't invalidate science, they expand it. But they also remind us that our knowledge has boundaries defined not just by technology or understanding, but by the very nature of reality. The limits of science also become evident in ethical and moral domains. Science can tell us how to clone a human, modify genes, or build autonomous weapons, but it cannot tell us whether we should. Questions of right and wrong, meaning, justice, and value transcend empirical investigation. They belong to philosophy, ethics, theology, and cultural debate. While science can inform ethical decisions by revealing consequences, risks, or biological realities, it cannot make those decisions for us. Ethical judgment requires reasoning that goes beyond data and experiments, drawing upon values, cultural contexts, and philosophical frameworks. Closely related is the question of purpose. Science is excellent at answering how questions. How does the heart pump blood? How does gravity affect matter? How can we transmit information over light waves? But it struggles with why questions in the existential sense. Why does the universe exist at all? Why is there something rather than nothing? Why do we suffer? Why do we care about truth, beauty, or justice? These are not meaningless questions, but they are not questions that science, by its nature, is equipped to answer fully. They demand reflection that blends knowledge, belief, and meaning in ways that transcend empirical measurement. Another significant limit is social and political. Scientific knowledge is produced by human beings within institutions, cultures, and historical contexts. As such, science is subject to the influences, biases, and power structures that shape all human activity. Funding priorities, institutional politics, and even cultural worldviews can influence which questions get asked, which results get published, and which areas receive attention. This does not mean that science is merely subjective or political, but it does mean that it is not immune to social dynamics. Recognizing these influences is crucial for maintaining the integrity of scientific inquiry. Moreover, the rapid development of science and technology often outpaces the ability of societies to fully understand or regulate them. Artificial intelligence, biotechnology, surveillance systems, and climate engineering all present cases where our ability to create outstrips our ability to foresee consequences. This technological acceleration can produce both profound benefits and unforeseen dangers. In such contexts, the limits of knowledge are not just cognitive, they are temporal. We often don't know what we've truly created until we experience its effects. There is also the issue of reductionism. Science often works by breaking down complex systems into their parts, understanding the brain through neurons, life through molecules, society through statistics. This approach has yielded extraordinary insights, but it also risks missing the forest for the trees. Holistic qualities like consciousness, identity, culture, or meaning can be diminished if we treat them only as the sum of their parts. Critics argue that science must be complemented by integrative ways of knowing, qualitative research, systems thinking, and even the arts, if we are to grasp the richness of human life and the world. Finally, we must acknowledge the role of ignorance, not just the ignorance that science seeks to overcome, but the deeper, enduring ignorance that might never be eliminated. Some theorists have proposed that there are inherent epistemic limitations to human cognition. Our brains, evolved for survival rather than absolute truth, may not be capable of comprehending every dimension of reality. Just as a dog cannot understand calculus, there may be truths forever inaccessible to human reason. This possibility is humbling, and it challenges any tendency to scientific hubris. Nevertheless, recognizing the limits of science does not diminish its value. On the contrary, it strengthens it. A mature understanding of science includes not only its power, but its boundaries. Scientists who acknowledge the edges of their knowledge are better equipped to pursue inquiry with humility, rigor, and responsibility. Science remains the most effective tool we have for understanding the physical world, improving health, advancing technology, and addressing urgent challenges. But it is one voice in a larger human conversation, one that must also include ethics, philosophy, history, and the arts. The question of where knowledge stops being science and becomes something else is not always easy to answer. There are blurry borders, interdisciplinary zones, and gray areas where different kinds of inquiry overlap. Fields like bioethics, environmental humanities, and science and technology studies illustrate how science can engage meaningfully with other forms of understanding. Rather than defending rigid boundaries, a more fruitful approach may be to foster respectful dialogue across disciplines. Ultimately, the limits of science are not failures, they are signposts. They remind us that knowledge is a journey, not a destination, and that no single method can answer every question. As we continue to explore, discover, and innovate, we must also reflect, deliberate, and imagine. Science is a vital part of that process, but so is everything that lies beyond its borders. In the 21st century, the landscape of science is evolving at an unprecedented pace. While the core methodologies of empirical observation, experimentation, and hypothesis testing remain central, the scale, scope, and structure of scientific inquiry have expanded dramatically. This expansion has led not only to deeper understanding within existing fields, but also to the birth of entirely new ones. The formation of new sciences today is influenced by a complex interplay of technological innovation, interdisciplinary collaboration, data availability, global challenges, and shifting intellectual paradigms. In this context, the question arises, how are new fields of science born in the modern world? And are today's scientists conscious of the fact that they may be founding entirely new disciplines? To begin, modern scientific research is increasingly driven by technology. As new tools emerge, be they high-throughput gene sequencers, large-scale particle colliders, powerful telescopes, brain imaging devices, or quantum computers, they open doors to questions and investigations that were previously inaccessible. These technologies do not simply extend our ability to investigate within existing sciences. They often reveal new layers of reality that demand their own theoretical frameworks, methods, and expertise. For example, the field of genomics emerged not just from classical genetics, but from the advent of tools that allowed scientists to read entire genomes rapidly and affordably. Genomics differs from traditional genetics in scale, data volume, and analytical complexity. It requires computational tools, algorithms, and statistical models, elements that pushed it toward becoming a distinct field. The same is true in neuroscience. While the study of the brain has long been part of biology, the sheer complexity of neural networks, coupled with advances in imaging and electrophysiology, led to the rise of computational neuroscience, a field that blends biology, computer science, physics, and mathematics. What started as an attempt to model neural processes turned into a robust area of study with its own journals, departments, conferences, and educational programs. A defining feature of many new sciences today is their interdisciplinary nature. Traditional scientific boundaries are increasingly porous. Fields like bioinformatics, nanotechnology, cognitive science, environmental science, and astrobiology represent intersections of older disciplines brought together by new problems or possibilities. These fields are born when researchers from different domains recognize that neither can fully answer the questions at hand alone. Interdisciplinary collaboration allows for the development of hybrid methods and the emergence of novel insights that give rise to entirely new domains of inquiry. Take artificial intelligence, AI, as another example. While AI research began in the mid-20th century, it was long considered a subfield of computer science. However, with the explosion of machine learning, deep learning, and large language models, AI has become a field in its own right, affecting not just computer science, but economics, law, medicine, ethics, and even philosophy. Theoretical AI, applied AI, AI ethics, and AI safety now form major subfields with different foci, methodologies, and objectives. In fact, the ethical implications of AI have prompted the formation of yet another emerging field, AI ethics, which lies at the boundary of science, technology, and philosophy. Another characteristic of modern scientific development is the role of data. The so-called data deluge has transformed how science is done. Fields like data science, computational social science, and digital epidemiology were not possible a few decades ago, not because the questions were unthinkable, but because the data infrastructure and computational capacity were insufficient. Today, petabytes of data are generated every day by satellites, sensors, social networks, and scientific instruments. The need to manage, analyze, and derive insight from this vast sea of information has birthed new scientific paradigms. Data science, for instance, did not grow out of a single parent discipline. It emerged from the confluence of statistics, computer science, and domain-specific expertise, driven by the necessity of extracting meaning from complex, large-scale datasets. Global challenges have also played a crucial role in the emergence of new sciences. Climate change, pandemics, sustainability, and biodiversity loss are problems that do not fit neatly within traditional disciplinary boundaries. Addressing these issues requires integrating knowledge from many fields: climatology, biology, economics, sociology, political science, engineering, and more. The need to respond to these challenges has led to the development of fields like Earth system science, global health, and sustainability science. These are not just interdisciplinary collaborations. They represent efforts to create new frameworks of knowledge that are better suited to the complexity of 21st century problems. What's notable is that in many of these cases, scientists are increasingly aware that they are contributing to the formation of a new field. The process is not always fully intentional or orchestrated, but it is often recognized as it unfolds. Conferences are created, terminologies are standardized, professional associations are founded, and academic journals are launched to support the growing body of knowledge. Graduate programs are established to train the next generation of researchers within the new paradigm. These are all institutional indicators that a new science is taking shape. However, the birth of new sciences is not solely determined by intellectual momentum or technological feasibility. Cultural, institutional, and political factors play a significant role as well. Funding agencies, university structures, and public interest can all accelerate or inhibit the emergence of a field. If a research area aligns with policy goals or attracts industry investment, it may rapidly develop into a recognized discipline. Conversely, promising areas may languish without institutional support. In this way, science is not a purely objective enterprise. It is embedded in social contexts that shape its development. The digital transformation of science itself has also opened new frontiers. Open access publishing, citizen science platforms, and collaborative digital tools allow for new forms of scientific engagement. Fields like digital humanities and network science represent attempts to study phenomena using tools and concepts that emerge from the digital environment itself. These fields blur the boundaries between science, humanities, and technology, and they redefine what it means to do science in the contemporary era. Moreover, as science becomes increasingly globalized, the cultural diversity of scientific perspectives contributes to the birth of new paradigms. Scientists from different countries and traditions may approach problems differently, bringing fresh perspectives that challenge established assumptions. International collaboration and comparative frameworks encourage broader questions and more inclusive research agendas, leading to fields that might not emerge in isolated contexts. It's also worth noting that the expansion of science today includes not only the birth of new disciplines, but also the reframing of existing ones. For instance, the integration of evolutionary theory with developmental biology led to the emergence of evo-devo, evolutionary developmental biology. Similarly, social neuroscience grew out of attempts to connect psychological theories of social behavior with neurological data. These hybridizations reflect an ongoing process of synthesis and refinement that pushes the boundaries of established sciences. In some cases, the question arises, when does a research area become a science? The answer depends on more than just content. It requires a community of scholars, a shared research agenda, accepted methodologies, and mechanisms for education, peer review, and publication. The emergence of these structures signals the transition from exploratory inquiry to established discipline. In conclusion, science today is a dynamic and generative enterprise. New fields are born from the intersection of technological innovation, interdisciplinary collaboration, urgent global problems, and intellectual curiosity. Unlike in earlier centuries, when the creation of a science might have been the work of a handful of pioneering individuals, today's scientific revolutions are often collaborative, distributed, and deeply embedded in institutional structures. Yet the essence remains the same: the desire to understand the unknown, to make sense of complexity, and to build reliable knowledge about the world. Whether or not today's scientists always recognize the historical significance of their work, many are indeed participants in the founding of the sciences of tomorrow. The emergence of science as a structured and methodical enterprise has been one of the most profound and consequential developments in human history. Across centuries and civilizations, from the speculative philosophies of ancient Greece to the data-driven models of the digital age, science has grown not only as a body of knowledge, but also as a way of thinking, questioning, and understanding the world. In this concluding section, we reflect on the core themes explored in the previous parts: how sciences are born, whether their creators realize they are founding something new, and what all this tells us about the nature of scientific progress and its place in our collective journey. First, it is clear that sciences do not simply appear out of nowhere. They are not spontaneous, disconnected bursts of insight, nor are they the work of isolated geniuses operating in a vacuum. Instead, the birth of a science is typically a process, gradual, cumulative, and shaped by a convergence of intellectual, social, technological, and cultural factors. This process often begins with a recognition that existing methods and explanations are insufficient for addressing certain questions. A philosopher begins to doubt traditional answers. An engineer notices patterns that no one else has quantified. A physician seeks to explain not just how to treat a disease, but what causes it. Such moments of curiosity and discomfort with the status quo often mark the early stages of a scientific revolution. New sciences often emerge in the spaces between or beyond older disciplines. These interdisciplinary zones are especially fertile because they allow concepts, tools, and methods from one domain to illuminate problems in another. For example, biochemistry emerged when the boundaries between biology and chemistry began to blur in the 19th and 20th centuries. More recently, neuroscience formed at the intersection of psychology, biology, and computer science. The reason these intersections are so productive is because they reveal gaps, places where existing knowledge falls short, and where new frameworks are needed to move forward. As we've seen, many scientists throughout history were not fully aware that they were founding a new science. Galileo, for example, likely saw himself as a natural philosopher in the Aristotelian tradition, albeit a rebellious one. Darwin viewed himself as a naturalist, not the founder of evolutionary biology as we understand it today. Even in the 20th century, those pioneering artificial intelligence or cognitive science were often unsure whether their work would remain a subfield or evolve into a discipline of its own. In some cases, the recognition comes later when institutions, journals, and academic departments crystallize around a new way of thinking. Nevertheless, there are also instances in which scientists have had a clear sense of their revolutionary potential. Newton famously declared that he had discovered the system of the world. Einstein was well aware that his theories of relativity challenged the foundations of classical physics. In modern times, researchers in fields like synthetic biology, climate science, or quantum computing often speak explicitly about building a new paradigm. This growing self-awareness may be due in part to the increased institutionalization of science, where naming and organizing a field comes with practical advantages: funding, visibility, collaboration, and educational programs. But why do sciences emerge at all? Fundamentally, they arise because human beings are confronted with complex, persistent questions that cannot be answered through existing means. The questions may be practical: how to build stronger materials, how to treat disease, how to predict the weather. Or they may be abstract: what is consciousness? What is the origin of life? What are the fundamental forces of the universe? Science emerges to address such questions in a systematic, testable, and explanatory way. And when the tools at hand are no longer sufficient, new tools, and often new sciences, must be developed. The institutional structure of science also plays a crucial role in its evolution. As scientific work becomes more collaborative and globalized, new sciences often require more than just good ideas. They need funding bodies willing to take risks, universities open to new departments, journals eager to publish interdisciplinary work, and a critical mass of researchers dedicated to building a coherent community. This institutional scaffolding is what turns a novel line of inquiry into a recognized discipline. It gives legitimacy to ideas, supports training for new generations, and enables large-scale collaboration that can push the boundaries of knowledge. Still, science does not exist in a vacuum. It is shaped by the societies that produce it. Historical events, cultural values, political ideologies, and economic systems all influence which sciences are prioritized, which questions are considered urgent, and which discoveries gain traction. The Cold War, for example, accelerated research in physics, computing, and aerospace. The COVID-19 pandemic galvanized virology, epidemiology, and global health. Similarly, the climate crisis has led to the rapid growth of environmental science, sustainability studies, and green technology. In this way, the needs and pressures of society can give birth to new sciences just as powerfully as intellectual curiosity. At the same time, science also reshapes society. The emergence of new sciences often leads to new technologies, which in turn transform economies, politics, and daily life. Think of the way physics gave rise to the nuclear age, how molecular biology led to genetic engineering, or how computer science revolutionized communication, commerce, and even relationships. In each case, what began as a theoretical pursuit eventually altered the human experience. This reciprocal relationship between science and society is both powerful and precarious. It requires careful ethical reflection and public engagement to ensure that scientific progress aligns with human well-being. The role of the scientist, therefore, is not merely to generate knowledge, but to participate in the ongoing shaping of history. Scientists are explorers, yes, but also builders of frameworks, teachers of paradigms, and stewards of human curiosity, whether knowingly or not. They contribute to the architecture of knowledge that future generations will inhabit. This is a tremendous responsibility, and one that demands not only technical skill but also philosophical depth, ethical integrity, and historical awareness. In today's world, where science moves faster than ever before, this awareness becomes even more important. Scientists now have access to powerful computational tools, global data sets, and collaborative networks. The potential to create new sciences, to redefine what we know and how we know it, is perhaps greater than at any previous time. But with this power comes the need for reflection. What questions are we choosing to ask? Whose voices are shaping the agenda? What assumptions are we importing into our frameworks? And how will our work be understood, used, or even misused in the future? To conclude, the emergence of science is not a static achievement, but an ongoing process. It involves the constant reevaluation of what we know, the relentless pursuit of new questions, and the courageous expansion into unknown intellectual territory. Whether through slow accumulation or sudden revolution, science grows because human beings remain dissatisfied with incomplete explanations. They seek coherence, evidence, and understanding. And in that seeking, they create, sometimes intentionally, sometimes inadvertently, the structures of knowledge we call sciences. In this process, scientists are both creators and inheritors. They work within traditions, build on the shoulders of those who came before, and push forward into the future. Their role is both analytical and visionary, empirical and imaginative. By understanding how sciences have emerged, and continue to emerge, we come to appreciate the richness, complexity, and humanity of science itself. It is not just a method, not just a body of facts, but a dynamic and evolving enterprise that reflects the deepest aspirations of human thought. Good night.